Hey everybody, this is Brad Dyke. How you doing? And I am reaching out to you to talk about something that's conceptual on NVMe. So, what is NVMe? Well, basically, NVMe is this little guy right here. This is a .22 variant of it, and this particular PCIe Gen 3 X4 is kind of important. Let me tell you why. So, the nature of NVMe clearly, very quickly, points out the limitations of PCIe version 4 and version 3. And the principal reason why is because it's so doggone fast that it eats up almost all the pipes that are out there. So when you start to put more than one or two NVMe hard disks into a system, it starts to degrade. And you're like, wait a minute, it needs to be like that fast. It was, but now that I got 6 of these in, or 12 of these in, or 24 of these in, what the heck? What happened? Okay, so the thing about that is, and I'll explain. I have to get my props here real quick. So the issue is there are 128-bit pathways for a traditional PCIe 4 or 3 version motherboard. And the thing about that is that this is its defining limitations. It's restricted. It only has so many pathways. And if you're using a 128-bit environment, you got 64-bit software, and you're running an exponential value of transfer rates. Having high I/O transfer rates is a wee bit of a challenge when you pretty much max out your PCI bus pretty doggone fast, which is a heck of a lot faster than SATA. So it is still pretty fast, but here's the problem. To make PCIe work effectively using copper, or in other words using wafer boards, circuit boards that the PCIe slots sit on, and so on and so on, the problem with that is they're defined specifically to the nature of that bus. In other words, it's made of metal. It's conductive, it moves signals through, it's binary, all that great stuff, but it's metal. I need 500 of these guys operational, and every one of them reaching their maximum output speed to reach the levels of compute value we need to be able to write to as quickly as possible. So how is that done? Well, it just happened. It happened this year, except I don't think they're thinking the way I'm thinking. This year, optical motherboards came out, quasi-style boards that use basically fiber optic-like communication. Now, I'm not saying there's fiber optic in the board. No, I'm saying that there's light in the board. And the transceivers that are on each end of that board are multi-frequency based. What does that mean? Well, you see, you can't do much with copper. You can make it better, you can better insulate it, you can do it, but it's still basically metal shoving electrons through the metal. Light doesn't have that problem. Light can just have small, minute variations in the brightness. We call those frequency variations. And each one of those can represent a data path. If I want true bidirectional 512-bit architectures for my data pipe, I need 1024 individual pipes. See what I mean? So if you were to create, let's say, I would say at a minimum, 8 channels of fiber optic pathways, and each one of them did 512 oscillations on each, you can pair those buses up and you give you basically 2 block 1024 pipes per every pair of fiber channel buses. Now, the end result of that is your controller still comes in, but those controller interfaces can actually go right into the fiber bus get broken up and sent out through thousands of data pathways, not hundreds. And you might have the avenue that you need to get NVMe finally off the ground and completely retire all forms of SATA and SAS technology, pretty much all forms of technology, on the older traditional spinning disk environments. Now, this is something I've been thinking about, and I've done many videos on this, explaining to people, who said, hey, I did this thing with a Raspberry Pi, and I've got my NVMEs, and it's blisteringly fast individually, but it's crap when you put 6 or 7 together into a RAID group of some type, or Z-RAID, or whatever you're playing with. And I explained to them the reason why is because of the limitation in the bus. You only have so many pipes that you can shove all that data through, and they can do a lot more individually, so they can really quickly use up a PCIe bus fast. So when is this technology going to come? I would say it's partially here now, but they're not thinking it that way yet, though I'm sure they will, because this goes with the strategy of the greater new nomenclature of the new processor generation, which will probably end up retiring the x86 environment altogether, and probably most of the other processor stacks we have out there, because you'll have a bigger die design. Still not very big, it's a normal size processor, but when they're burning at 2 nano and 1.2 or 1.5 nanometer designs, they can put tremendous amounts of RAM into the die itself, terabytes of resources. All they have to do is to change the latency. In other words, force the levels of storage or memory capacities to be slower and to take different roles. And then the CPU has all of its data, including your boot drive information, all in the drive. And the only thing you need now is one standing 16550 UART output for your pairing interfaces for analog, one USB chipset designed for handling your USBs, and then this gargantuous, awesome fiber bus. And that would be probably the best way to call it, is a fiber bus. And as time will go, those fiber buses could be huge. And everything that connects to those is at unprecedented communication levels. The only thing, of course, that is a problem is the arrays. The arrays, once again, become the bottlenecks. Now, what am I talking about? Let me explain. When IDE and SCSI and all those kind of storage arrays came out, and they had functionality, the key thing about those drives is the nature of the drives themselves are pretty doggone fast, and the controller was the bottleneck. Over time, the controller got faster, and the storage arrays became the bottleneck. Over time, back and forth, back and forth. Now we have a new player back on the table, and that is that when we have ourselves the next generation fiber channel, or I'd say fiber bus communication platform, and these cards are put in, like 10 or 15 of these cards are put into your system, and they may not look like this at all, by the way. They might actually just be a very small edge connector, because if you look at an NVMe, it has a very small edge connection as well. So lower voltage means you can reduce the connection points on the card sets, but they plug up and they go in and they become communication endpoints. And what ends up happening is, yet again, the bus is giant once again for the motherboard, or what we call an I/O board. The controllers are not the bottleneck now, because they get full channels. They get all the bandwidth they can use. And then the disk arrays become the slow poke because of two reasons. One, the disk array is detached from the bus. And two, it could be detached by feet. Because if you look at a rack enclosure, that's 5.5, 6 feet in height. And you can see there are disk enclosures above and below, and every inch of those cables, that's right, communication cables, every inch has a latency effect. That's why there's expectation when it comes to dealing with our environments, and we know those mathematical equations when we design platforms. Now, today corporations usually don't pursue storage capacity like they used to. That's because the life cycle has changed. In the nature of software and hardware, the life cycles have exponentially been reduced by zero point 0.2. So every time we hit a life cycle of a hardware, it gets a little faster. Okay? And then it gets to the point where that becomes a nomenclature and a new type of platform is created. And once again, the life cycle is fairly lengthy, but it will speed up over time. We see this happen quite a bit. An example is x86 baseline processors were replaced with MMX style processors and extended computation processors and Xeon processors and so on. And these are life cycles of that model. Software, on the other hand, goes faster and exponentially faster than you or I could probably fathom, because what took 3 or 4 years to accomplish code updates was reduced to roughly 6 months, and then from 6 months to 3 months, then from 3 months to 1 month, and from 1 month to a couple of weeks. And that's kind of like where we're at right now. We're getting updates. If you're in a Linux environment, you're getting updates usually in scale every 2 weeks. And so, yes, the life cycle of hardware isn't as fast as software, but that's important because software has 35 years to do, catching up to do. And so that's how it's going to get to where it needs to be, by the speeding up cycling. What do I mean by that? Well, hardware is only as good as the software that uses it. And that was a major imbalance in this industry for many, many years. We just kept going out there and buying faster hardware because it was inheritive. In other words, you would get something a little bit nicer, a little faster, a little bit more functional, but you get zero benefit in the software because nobody's writing the software to take advantage of the new chipsets, because they're still trying to write the software for the old version, and so on and so on. That's kind of changed these days. Finally, we're seeing software catching up to everything PC-wise or server technology-wise, and that's a good thing. So it comes back to the nature of how do we get 500 NVMe disks running at 80 to 90% of their potential, and the avenue to that is, well, if we can successfully get fiber busing on motherboards, we got it covered. And we got it covered in spades, because there are thousands of frequencies that light can function in. And I think we're going to discover that's going to be a new precedence in our industry in general, because it just gives us a tremendous boost and almost an infinite value of handling of I/O. That's when you can start doing 8K renders in real time. This is serious stuff, and the only thing it inhibits is the bottlenecks. And they'll always be present, but this is definitely probably one of the most positive approaches I've seen in a long time to get to that next level. Unless, God forbid, a vendor comes in and attempts to lock up some part of that technology so that they can have the monopoly for a period of time, like EMC did to storage arrays in the 2000s and so on. Unfortunately, EMC did tremendous damage to the IT industry when it did that, because it bottlenecked and stifled innovation. And they made billions of dollars, and when they finally realized everybody caught on, oh, they sold that company like that. They got it out of here, and they were moving on to nothing but vacations and relaxation and all that good stuff. Dell, of course, bought EMC, and when Dell did that, Michael Dell, he's always had a really good strategy about open-ending technologies, and boy, that again, innovation started coming in. And of course, there's always that struggle of profitability versus innovation. One's got to pay for the other, right? But there's also a point of where you can cut innovation off completely by trying to dominate a specific type of technology, which I hope this time does not happen with this, as the fiber optic communication nomenclatures are transferred into a photonic style communication bus, and using photons, which are so much more capable than electrons. And with that being said, there's also something else that is coming down the road, which is very impressive, and that is an optical style drive that is still in development, capable of doing petabytes of environments. And think about it. If you have your data in optical media, EMPs can't do anything to you. If your equipment is based on photonic energy, light, then all it needs is electricity to power the principal components of that system. You can EMP the hardware pretty effectively, but data being stored in magnetic volume, not a great idea, because EMPs can affect electromagnetic fields. But optical fields, which are read by optical systems like lasers and so on, don't have that problem. So data is present and it exists. The only other way that you could possibly make it any better is to be able to take a pair, or let's say 4 electrons, 2 charged negative, 2 charged positive, and turn them into binary bits. And they sit there and they spin themselves in space, representing a bit. Now you're thinking, well, that's a heck of a lot of work for 1 bit. Yeah, but you would spew out trillions of these, as you would spew out with anything. And because they're in sequential order and voltage loads, you would be able to travel through them by frequency variation modulation. It would be like watching film. You know, each slide, instead of it being one order after another, it's in frequency. So one frequency, the next frequency, the next frequency, the next frequency. And you just slide up the frequency and you can watch a movie. Just like you would spin the roll of film in a projector. Anyways, there are a lot of potentials out there, but we need real bandwidth, and the industry is kind of stifled until recently, and we got to give them a little bit more time to kind of get it structured and in a good place. But I think it's finally something I can see a path to getting over all of the loss of performance when you're doing a lot of these NVMe drives at once, because that's just it in a nutshell. Next video I'll do in the hardware environment is showing you how to break the box. You know, you see that little guy right there? Well, he's a hard drive. Isn't that cool? So, and he sits on a SAS bus like it's nothing. Super light, super efficient. This was designed to hold a 2.5 inch drive. Now look at it. So we're going to talk about miniaturization for the sake of miniaturizing. Not for speed, not performance. Remember, I already talked to that video. But more for get it smaller so that you can put it in a little case like this and walk around with, you know, a couple of terabytes of capacity, or in this case, probably, I don't know, 25 terabytes in a very small device. So, but with that being said, this is Brad Dyke signing off. I hope you enjoy the video, and God bless, and take care. Bye-bye.